so we'll still go on. So now imagine, so spin half, okay? And let's say, so m sub I plus half minus half, and then we call, so number of nuclei, since this is plus half, we call it n plus, number of nuclei in this m sub I plus half level n plus, and likewise this one n minus, okay? And so total number of spins, so n total number of spins n is n plus n minus, and we'll also define another quantity small n, which is the excess population in one state compared to the other, n plus minus n minus, okay? By the way, speaking of this chalkboard and all, so last semester I was teaching a class of 350 in LA classroom, okay, first year course, mechanics. So there people are sitting, kilometer away. So obviously you cannot use the chalkboard, nobody can see. So there, this thing is fantastic. So there are many things you can do. So of course you connect laptop. I mean, although I don't like this PowerPoint slide and all, it's not a good way to teach, but you were just forced because of just the numbers being so large. But the great thing you can do is, it projects to big screen up. And you see, on chalk, the visibility from a bigger distance is not great. But on this one, since it's lighted, the visibility from a far distance is also very good. And in those classrooms, what you can do is, on one big screen, you can have what's on your laptop PPT slide. And then there's such a thing also available, you can write on that, and that's maybe projected on the other one. So you can state the problem, work out some things, and I mean, the experience is different. So small classes, it doesn't matter, I guess, this or that. But bigger classes, it makes a big difference. Yeah, so what we are interested is, right now, we said you have a sample, you have system, you have nuclei with spins, and so some occupation of the ground, simple case of spin half, so some occupation of the ground state, some occupation of the excited state. And then there are two ways you can get transitions. One is, of course, you have some matrix element which causes transition between these. That's the external AC field that you apply, okay? But also you have the so-called lattice present. And then you will get, if there is an interaction term with the lattice, then you will get some transitions between these states, okay? So we'll consider both of them, but first, so we just have an AC field, let's say. Okay, so right now, we are not talking about the lattice, we're just looking at transition between this because of the AC field. Okay. Then later we'll put the other one also and then see, it's really finally a combination of the two in a real experiment. Okay, so this AC field causes transitions. And let's call, say, W plus to minus as probability of transition from plus half to minus half. Okay, and likewise, one can define the opposite one also, W minus to plus, and that's again probability of transition from minus half to plus half. So if you have more complicated systems, spin 3 half, 5 halves or something, then you'll have so many levels and accordingly transitions between those pairs of states, etc. So that's later if needed. But the concept, to get the concept of what's happening here, right now this is okay. So you just define these two as probabilities, and then we write the equation for rate of change of population. So you have these transitions possible. So of course the populations of these states is going to change. So let's say dn plus by dt. So at what rate is the population of this ground state going to change? That is because you have some number of nuclei in the upper state and they're going to transit to the lower state. Okay, so this multiplied by W minus going to plus, right? But also you will have decrease of n plus because of the other transition. So that depends now on how many are there in this plus half state, and then what is the probability that they go to the higher state. Okay, and for this situation where you are ignoring any contact with the lattice, it's just transition between these two levels here. Firstly, the transition probability is just given by the Fermi-Golden rule, and for us, both these probabilities are equal. Okay, just because the matrix elements are square of the matrix element is going to be the same. So this probability of transition is just 2 pi by h bar square of the matrix element, right? So in general, some Hamiltonian between states A and B squared, and then you want to take care of energy conservation. So EA minus EB minus h bar omega. In general, between two states, you have this as the transition probability. Okay, and you know, for our kind of problem, P A to B is same as P B to B. Okay, because whatever is our matrix element here, complex conjugate, all that doesn't change, and then square of that, so it's the same. Going from ground state to excited or excited to ground, it's the same probability. Okay, so what we'll do is we'll just call this W. Okay, so this W plus to minus or W minus to plus, we will just call it W. Okay, so what we are interested in is how does the population evolve, but it's convenient to see how the population difference evolves with time. Okay, so one can rewrite this. So you have dn plus by dt, and likewise you can write dn minus by dt, right? And we'll just quickly do that. So if you just combine, you write, you have a dn plus by dt. Now this saying it is equal to w with the transition probabilities, then this is just n minus minus n plus w. Okay, and then what you can do is you can write also dn minus by dt in a similar manner. Okay, and it's very clear what to do. If you're doing dn minus by dt, then you're counting increase of the population because of transition from the plus state. Okay, so it will be n plus with a positive sign times w, and then n minus with a negative sign. And then if you combine, and keeping in mind that we define these new variables, the n total is just the sum of n plus n minus, and the difference in population is small n. Okay, so if you do that, right, so it's fairly straightforward to see what you have to do, because this can already be written as minus small n times w. Okay, likewise if you do dn minus and then look at their difference, okay, right, then again the left side you can written as d by dt of small n basically. And so it's fairly easy to see that you get, so the population difference, how does that evolve? dn by dt is minus 2w times n, right? So you'll get a minus w times n from one and also from the second one. Okay, so you'll get n as some n naught e to the minus 2w. Okay. So if you don't have any lattice or any interaction with the lattice, and you have this AC field, eventually the population difference will become 0. Okay, you start out with some initial condition, whatever it is, and then with time this decays, and so I mean at t equal to infinity, this becomes 0. So you start with something and exponentially it goes to 0, so you get equal population in the two states. Okay, if you don't have any lattice to deal with. Okay, so yeah. So next, actually, we want to also take into account the fact that there is a lattice. So how does that change things? In a real experiment that we do always, of course, you have a AC field which is causing these transitions, but you also have a coupling with the lattice, which is also driving transitions between the two states. And it's a combination of these two which will determine finally what is the population difference. Okay, so let's just see how that happens. So once again, in terms of notation, so let's say, so in the previous case, once you are in equilibrium, the populations are equal. N plus, N minus are equal, as we see. Now, when you are going to have coupling with the lattice, we expect they will not be equal. We'll just see how that's the outcome of the equation, that's the solution, but we'll see how that happens. So you have, let's say, you define N plus 0 and N minus 0 as equilibrium populations of the plus minus half level. So these are the equilibrium populations of plus half and minus half level. So now you have some lattice, you have a temperature of the lattice, and now, earlier you didn't need to define any temperature. Okay, it doesn't matter, you have just two levels, only transition between the two, so finally no population difference, whatever you start with. Now that you have some coupling with the lattice, and then the result, so that's like a bath, it has a temperature. So just by following Boltzmann distribution, the population ratio, right, of the higher state to the lower state is given by this Boltzmann factor. Okay, that just StatMech.
So why not Fermi Dirac?
Yeah. So it's not necessary to treat these as quantum mechanical. It's not particles really. It's if you think of StatMech, then you think of this canonical distribution, canonical partition function, canonical ensemble. Then you basically try to count how many particles you can put in each state following some rules. So, so in principle, there are only two possibilities, because particles are either fermions or bosons. Okay, and so it's either of the two occupation probabilities that are correct, right? The bosons and the Fermi-Dirac. However, if you are in the so-called high temperature limit, right, both these distributions, 1 over e to the minus ef by kt plus 1 or similar one with the minus 1, both go to the classical Maxwell-Boltzmann limit. So it turns out that here, whatever is this energy difference, so it's possible to consider it in the high temperature limit. Okay. So therefore, this is okay. You don't need to consider the quantum nature of the particle.
we can say which temperature we are dealing is the KBT energy is larger than their difference in energy.
Yeah, much larger. Yeah. So of course, if you go to really different experimental situations, then things might change. But here, for almost all the treatment that you do, you can treat this in the high temperature limit. So what is the energy scale of the problem, and how does that compare with the thermal energy? So
like Fermi function, we consider 0 to 1 like that.
Right. So it's like so the Fermi function is something like this, where you have to watch out at typical temperatures. This is, so we are looking at let's say Fermi-Dirac distribution function as a function of energy, and this is like the chemical potential, more familiar with the term Fermi energy. So whatever typical temperatures that you do your physics, do your experiments, this is always much greater than here. So I mean, the outcome of that is I'm sorry, the other way. So different things apply for different situations. If you treat a typical metal, you are always in the situation of KBT much less than EF. Right? Just to remind people, EF is of the order of, in EV. EV. Yeah. EV in units of temperature. Right? So so EV is of the order of 1000 to 10,000 Kelvin. 1 milli EV is about 11 Kelvin. Okay. So 1 EV is then 11,000 Kelvin. So the typical Fermi energy, so how much this is, and typical temperature you're going to do measurements is 100 K, not even 1000, things will melt by that time. So several hundred K, which is much less than 10 power 4. So usually you are in a situation where, this part is what contributes to any properties. So you don't need to consider states which are well below the Fermi level. It's only those states which are just in some narrow range here which contribute. So this is like the extreme quantum in some sense. So metal at room temperature can be treated as a Fermi gas at 0 temperature, where you really have to consider the quantum nature. Okay. In contrast, here you are the other way. So how does this evolve with temperature? Suppose you could go to tens of thousands of K, then this is still 1, but it like becomes like this, right? As temperature increases, and so you're almost just exponential all the way from 0. I mean, it should diverge and all, but basically whichever range you're dealing with, it's just exponential. So the issue is, what's the thermal energy? How does it compare with the energy scale in your problem? Okay, typical metal, even at room temperature, you can treat it as a Fermi gas at T equal to 0. Okay, and your answers are not wrong, they're almost correct because of this reason. Can make similar arguments with the Bose gas also. In contrast, for this problem, whatever are energies of the problem and whatever is the typical temperature, it's the other limit that is applied. So this is still correct. You can apply just the Boltzmann distribution to calculate the population difference between the two. You don't have to consider what statistics is obeyed. It may be spin half, spin 1, doesn't matter. So this T is of course the temperature of the lattice. Then once again, like before, we want to look at what is the transition rate. How does the population change, right? Earlier also we wrote down dN by dt, and then you had these rates, and then once again the population difference, how it evolves with time, we wrote down. So in a similar manner, we again want to do that. So dn plus dt. Once again, you have those which are in this minus level, but they transit from minus to plus. So we indicate that by a W with the arrow down, right? Remember, we have minus half and plus half. So n minus in the upper level, n plus in the lower level, and the transition going up to down, we call it W down, and the other transition going from bottom to top is W up. Okay.
I forget why we looking these transition rates. Just a reminder.
Why?
Why we looking these kind of transition?
Yeah. We want to finally write down what is the rate of change of this population difference. We want to write an equation. So how does that evolve with time? And later, in an actual problem, when you actually have a lattice and you have nuclear spin sitting in a lattice, and you are applying a RF field. So what should be the governing equation which will tell you how the population changes? That's what we want to get at. So we want to take care of both these effects. The fact that you applied a RF field which is causing transition, but also there is some coupling with the lattice. Lattice is at some temperature, and so that is also driving some population difference, and we want to take that into account also. So this is one part, and another is of course n plus with W up, right? So whatever you have in the plus state, but it is going away, so there's a decrease, so therefore a minus sign. Now, unlike the previous case where there's no lattice, you just had transitions with two levels because of the RF field, there the transition matrix element was the same. So those rates were the same, but not in this case now. Because if that were the same in this case, then this dn by dt will be 0 in steady state. Okay, so this situation where you are just taking care only of the lattice part is different from the earlier one. So this W up is not equal to W down, because you need to have this kind of population difference in equilibrium. This is mandated by some StatMech ideas. So the end point is clear. But if we had the rates to be equal, then the populations would become equal, like before. But we know that's not the end point. So the W up and W down have to be different. And given this condition that the population, see, right, with the 0 here saying it's the equilibrium population ratio, if this has to be the equilibrium population ratio, then we'll find out what is W up by W down. If W up is equal to W down, then in equilibrium, this is 1, right? We did that earlier. Now the other way, we know that in equilibrium, finally, the ratio has to be not 1, but exponential minus delta E by kt. So now we'll work back and find out what should be W up by W down. Okay. So just like before.
Right now, sir, RF and lattice both are there.
No, right now only lattice is there. Then later we'll combine the two, as if one plus the other, just superpose them. Okay. So first one was with only RF, no lattice. Second one with only lattice, no RF. Okay. So once again, it's very easy to do. Once again, you define n plus minus n minus as the population difference, and n plus plus n minus as the total population, capital N, and you can again rewrite dn minus by dt in a similar manner, flipping signs and changing the w's also, and if you then subtract, then on one side you will get d small n dt, okay, and just run the algebra for a couple of steps, and what you get, because the population in equilibrium is known, so what you get is W down by W up. How the transition probabilities are different for up to down versus down to up, right? Ultimately, you want more population in the ground state. Okay, so their transition rates must be different, and this comes out to be e to the gamma h bar h naught. Applied field is there, the Zeeman effect is there, so it's creating these levels by kBT. Okay, so this is one thing. And the other thing, I mean, this is just determined by what the equilibrium population ratio is. Right? So once the ratio of these rates is known, you can sort of put that back in here and then do your dn minus dt and then take the difference or d small n dt, etc. Right? So small piece of algebra you can work out. And if you do that, I skip few about a page of algebra, but what you get is dn by dt is n naught minus n by t1. Okay, where so this is what you get, where, as I said, there is no RF field, but lattice present. Okay. Yeah.
I have a question.
Yes.
How does this population inversion get created because of this lattice?
It's not inversion here.
Like a difference.
Yeah. So, I mean, we are sort of working the other way. If you have a bath at a temperature T, and there is some way to exchange energy between the spin system and the bath, then ultimately the equilibrium population ratio has to be given by this Boltzmann function, Boltzmann factor, right? This you're happy with, right? It comes from some generic argument, Statman. So if that is the case, then W down cannot be equal to W up. Otherwise, you will get zero ultimately population difference. Okay, so if that is the final situation, then you can, with little bit of algebra, you can find out what is W up, W down by W up, which comes out to be this for energy level difference just given by mu h. So gamma h bar h. Right? So this is derived by knowing what the final population ratio is, which comes from some generic Statman rule. Okay. So ultimately, there has to be, I mean, because of the sign here, if you have something at a temperature T, you have a bath at a temperature T, then it's clear that population of the higher level, like n minus is the higher level, is less than the population of the lower level. So not inversion, but the natural population is more populated of the ground state, less population of the excited state. Sort of makes sense also. If you go to T equal to 0, then there are no thermal excitations, then everything will be in the ground state. So it's sort of intuitive also.
It's like due to the temperature exchange between the lattice and the nuclei.
It is because of energy exchange between the lattice, nuclei and the lattice. Yeah. Because ultimately that temperature T has to be maintained. Yeah. So if that, I mean, there's no you can intuitively think about it like this: if there's no thermal energy present, then everything will remain in the ground state. Okay, the lattice cannot take up anything then, so everything remains in the ground state. If you start out with everything in the ground state, it remains in the ground state. I mean, maybe that's the way to look at it. If you start out with somehow some population difference, it will remain at that. Nothing will happen.
So can we create the population inversion like we do in the lasers here?
Precisely. Yeah. So when you then apply an RF field, this is exactly what you do. It's up to you. You have it long enough, you will pump everything from the ground to the excited state. So exactly, NMR is where you create a population inversion. You start out with this population ratio, no inversion obviously, n plus is more than n minus. But now if you apply an RF field, you are externally driving, so you can pump nuclei from the ground to the excited state. And it's a transient thing, but if you apply RF long enough, everything will be at the excited state. So again, we're going ahead, but if you have an RF field continuously, again, quantum mechanically one works out the problem. Have you heard of this thing called Rabi oscillations? Okay, so Rabi oscillations. So that's exactly what will happen. If you have the two levels and you are continuously on the RF field, you will excite nuclei, so you will get a population inversion, and with time again it will go the other way, you will get all the population in the ground state, it will keep happening forever. Okay, these are called Rabi oscillations, we can derive it of course. Okay, so yeah, you do get population inversion if you have your RF field on for a certain amount of time. Again, there are classical equivalents which are very intuitive also, so we'll look at that. So yeah, so this is now the this was the rate ratio, and this is now the equation for how the population difference evolves with time, and this T1, so W down plus W up, this is defined as 1 over T1. Okay, you have some rates for going down and going up from the nuclear levels, and this combination, so they tell you about the probability of transition, etc.
When we are talking about population inversion, in that case we say that two-level lasers don't exist. Means in two levels transition will not take place.
So in the sense there you need some other state to, you want to maintain the population inversion for some time. So maybe in that context you say two-level laser doesn't exist. You need some other level to hold the population or something, right? So here there is nothing like that. You have two levels and then you'll get population inversion. It's not permanent. I mean, if you wait, then again, if you have the RF field on all the time, then because of the Rabi oscillations, you'll again have population going down, again going up, that we'll see that will continue. So if you encapsulate this thing which tells you at what probability of transition up to down and down to up into one parameter, okay, then so the algebra to go from the previous one to this, it's just about a page, you can do it yourself very easily, so but please do it. Then the equation that you get is like this.
So N naught, what is
So equilibrium population difference.
okay.
N plus 0, so N naught is N plus 0 minus N minus 0.
Yeah.
And N is the dynamic one. Okay, this T1 is called the spin lattice relaxation time. Or often the rate, 1 over T1 is the spin lattice relaxation rate. So the spin refers to nuclear spins, and lattice is a generic term. So whatever is the bath it is in, that's called the lattice. It may not always be the physical lattice. In at least the kind of NMR we do, we are often interested in a situation where this so-called lattice is really the magnetic moment, the electrons in your system. That is the lattice. You have some energy exchange between the nuclear spins and the electron spins. So you have an indirect way of probing the electron spin fluctuations via monitoring the nuclear population, what equation that follows. Okay, so what is the lattice? Lattice is in quotation marks. At least in our research, we are largely interested in a situation where the lattice is this, the magnetic moments. or free electron, depending if you have a metal. Then so magnetic moments, or if you are talking about a metal, then free electrons. Okay, but in general, this is one possibility. This is another possibility. The actual physical lattice is also a possibility. If you have some, see, you need some transition matrix element between the two, isn't it? Only then you will get the transition. So you need the nuclear spin system to lose energy, but then something else must take up the energy. So that something else can be the magnetic moments of your free electrons, the free electrons, or the actual lattice also.
Sir, how it is possible, because electron magnetic movement is larger compared to nuclear magnetic movement. So how you relate that particular amount of energy is transferred to?
So you need to know. So for free electrons, for example, you have some energy level scheme. You have field level, still Fermi energy, and available states above that. So whatever, I don't know, micro EV loss you get in the energy of the nuclear system has to be taken up by, you have states available just above also. So it has to be taken up by the free electrons. Size of the moment is not the issue. What is the energy level scheme is the point. Okay. So here, what is the excitation spectrum for these magnetic moments? Okay, that's the issue. And so by losing energy in the nuclear system, you need to take that up in the spin system. And so it depends what the, so it depends on what the, people who are doing NMR know this, dynamical susceptibility is further. So you have something called the fluctuation dissipation theorem, which you might have learned. So fluctuations in the lattice here, spin system or the electrons, give rise to a dissipation in the nuclear system. So you need dissipation, you need loss of energy in the nuclear system. That is taken up by the.
Can we say it's a relaxation between two systems? It's the word is.
Relaxation because the nuclear system is coming back to the ground state. So that's why relaxing back to the ground state from some excited state you created because of the RF field. Okay. So it can be the lattice also, but of course you need some matrix element which couples the spins, nuclear spins with whatever other agency. Note that always, what is the final effect? Even if it is these magnetic excitations through free electrons or magnetic moments, finally they will also connect with the actual physical lattice and lose energy to them, giving rise to a rise in temperature. So final bath is that anyway. Okay, so that's not something you measure or monitor all the time, but it's really the relaxation is nuclear spins. So energy from nuclear spins going to so-called lattice, but that could be just magnetic excitations. And you might have some weak coupling with the actual lattice, crystal lattice. And so ultimately, whatever energy loss takes place in the nuclear spin system, you have plus half, minus half, whatever the energy level difference, you relax nuclei from excited state to the ground state, that is finally taken up by the actual physical lattice. And so actually it should give rise to an increase in temperature of the lattice because of this. You put in energy from the RF field. It's taken up by the nuclei. They come down, that is taken up by the electrons. Then they come down, that is taken up by the lattice, giving rise to heating. Okay. We are usually monitoring only this part. This happens at a rate 1 over T1. Okay.
So what if there are no states available for the electronic system, like if it's an insulator?
Yeah.
So in that
Yeah. So then what will happen is that the T1 will be very, very long. So, okay, this is another thing. I mean, those who have actually been doing know this. So what is the value of T1 typically? Again, sort of from a practical viewpoint, right? If if you take typical metals and those where there's sufficient magnetic excitations and a good coupling and all, so typically several milliseconds, 1 to 10s of milliseconds or somewhat more, okay, milliseconds to hundreds of milliseconds maybe. But if you have really insulating material with no magnetic moments, no free electrons, then it's really only the physical lattice which provides this possibility of energy loss. Then, so this is in a typical case where there is some magnetic fluctuations. But if you don't have any magnetic fluctuations, then this value can be like hundreds of seconds or more. So I don't know. Monica, you measured sometime in a non-magnetic compound where
100,000 seconds.
Even I remember with Dhanshekar we measured something in a non-magnetic one just to get some baseline. It's very long. Then any small impurities and all these things will actually dominate and they will give the relaxation. But yeah, so agreed. If you don't have any fluctuations present, and also once you go down in temperature, all these thermal fluctuations, all that also dies down, and so this can just become very, very large.
But since he is asking about insulators,
Yes.
our systems are also insulators.
No. Charge-wise, insulators, they're not conducting, but the magnetic excitations are present. So, right, so you're looking at local moments, there's dynamics involved there. There are fluctuations happening, and then there is coupling to those fluctuations. And so you get small enough. But even that is not there, your non-magnetic analog. With the copper you replace by some magnesium or zinc or something which is non-magnetic. Then there are no moments and then there is no mode of relaxation. Yeah.
So one other question. So the RF field that we're applying,
Yeah.
so we're saying that the nucleus is taking that.
Yeah.
But equivalently, the electrons can also be perturbed by that same RF field. So then, how do we distinguish between these two?
Yeah, we will see what the values of this energy are. Yeah, question is, you have. So I'll do a quick answer, then detail also we can answer later. So, first point. So this energy level difference, right? So gamma, h bar, h naught. Okay. So this is now the nuclear gamma. Normally h bar by, for electron h bar by 2 mc and all. So inverse the mass. So typical energy level difference for electron will be 1,000 times larger. If you take just free electron spin half, then Zeeman, with applied field you get Zeeman splitting. Now that energy level difference will be at least 1,000 times larger. So with the RF fields that you apply, the frequency that you use is not sufficient, that energy is not sufficient to excite.
Hence it acts as a bath.
It acts as a?
Bath.
It acts as a bath, exactly, yeah. And then that's what we are probing. We are probing that indirectly. Yeah. So, so if you now incorporate both the effects, so the effect of the lattice as well as because of the RF field you have this transition between the states, then you get dN by dt is minus 2W times small n. So that's what we wrote down over here, a couple of pages back, 3 pages back, just to show you. Right, so this sort of equation, and we just call this 2W, okay. And so putting together the effect of RF field plus right. So this is the one related to the no RF field. So no RF, only lattice, and then this 1 over T1 is, remember, W up plus W down. Okay, and on the other hand, this other one here, this part here is so RF present, but no lattice. And this W is actually, so remember in this case there's a W up being different from W down. In this case they're equal, right? It's just the H1 field which is giving rise to transitions. And so this is just the transition probability, so it's written as some W. Okay, so the W represents transition probability because of the applied RF field. Okay, this 1 over T1 represents transition probability because of the spin lattice coupling. Okay. And so now once again, if you calculate what happens in steady state, so as time goes to infinity, in steady state, you'll get n as n naught by 1 plus 2W T1. So it sort of now depends, there's one more parameter now, because you have now a transition because of the RF field part, at what rate that happens, and then another part because of the spin lattice coupling, which is part of the T1. So suppose in the denominator this 2W_T1 is small compared to 1, then your population at the end is just n naught. Okay. But then, okay, it depends on the detail. So depends on the value of, if you have a weak RF field, then this is the case. By increasing the RF field, you're basically increasing W, right? Remember, this W represents transition because of the RF field, and so you can change this condition, and then n equal to n naught will not be the equilibrium case. So if
so in our systems n equal to n naught.
yes. Okay. So
Sir, if we are using strong RF field, but the T1 value is very much lower, maybe due to the magnetic fluctuation, then it will be n equal to n naught or not.
So you have different possibilities now. Firstly, once W approaches, because of this equation we're writing it like this, once W approaches something like this, so W I can keep increasing by increasing the RF field. T1 is there, I have no control over it. It's just internal, what is the coupling between the spins and the lattice, that determines the T1 for a given material. This I can externally keep increasing by increasing the applied RF field. But once this condition is reached, then you can get no more energy absorption. You have to see a little bit of detail because this validity of the condition is only for this n equal to n naught only for this situation. By increasing transitions, by increasing the RF, you increase energy absorption, but then once you reach this limit, you cannot increase the energy absorption anymore. Okay, so if T1 is really long, then you even may not be able to get a population difference to be able to attempt NMR. So originally when NMR was discovered, this was one of the challenges. I mean, some people were lucky, they used samples where there was sufficient coupling, and so you could get a population difference. Otherwise, to start with, to get a population difference, to magnetize a sample. If you take usual sample, magnetize for electrons is one thing that that you call a magnet, but to sort of magnetize a sample for nuclear moments to create a population difference, you need a T1. Otherwise, you will not get. No, you need a bath. So if they're not talking with each other, then the population will remain equal. You will not get a. So where's the question of doing NMR then? Okay, you need a population difference to start with. So yeah, there are a lot of issues. We are always dealing with situations where, in practice, where T1s are there, short enough that you always get population difference, and then you can attempt resonance and obtain a T1 finally, which tells you what the fluctuations of the electron system or the magnetic moment system is. So what we try to do next, I can go on for 10-15 minutes. So we'll try to do now two things. So the question is, I have magnetic moment, nuclear magnetic moments. I have a DC field, okay, and on top of that apply an RF field. What happens? What are the dynamics of these nuclear moments in such a situation? Okay, so there is a classical approach to this.
And this RF unit is precisely very little noise control, very finely noise control.
So you have a function generator. It gives a sine wave.
It's a simple DSO kind of setup, or like you generate RF?
I'll talk about the technical parts. I'll talk about that at a later time, right? Yeah. So yeah, you generate precisely a frequency. You get electronic instrumentation, no problem. Yeah. You need a frequency synthesizer giving rise to a particular frequency, and then what do you vary? Do you vary the frequency? Because you have some energy level difference which depends on H0. So let's say H0 is fixed. Now to observe a resonance, I need to change the energy of my RF somehow. So I need to change the omega of the RF. Is that what is done? How do we do it? I'll talk about that. Okay. What was done in the early days in the classical times, and then how that changed over because of new instrumentation and all. We will talk about that. So yeah, we'll do a classical approach. So you put a magnetic moment in a field, then how does it respond? So the approach is very straightforward in the following way. You imagine these magnetic moments as something having not imagine, I mean quantum mechanically it is already there. They have a spin angular momentum. Okay, right?
Yeah.
They do. So if I apply a field H0 and I have a moment mu, which is then related via gamma to J and by another H bar to the I, right? So moments have a spin angular momentum. Okay, this we know quantum mechanically. So you can imagine for classical part as if you have spinning top basically. You have something with a spin angular momentum, and in a gravitational field, for example. Here you have spinning moment in a DC field. Okay, you have probably done this problem in classical mechanics sometime.
Yeah.
Yeah.
Very common.
Yeah, spinning top in a gravitational field, for example. No, you would have done, nahi? Okay.
I think I forget.
Okay, doesn't matter.
Larmor precision and all.
Sorry?
Larmor precision.
Larmor precession, yeah. So what are the dynamics? So again, I'll write the answer already. So you will have if you have a magnetic field, then there is a torque exerted on the moment.
Oh, gyroscopic motion.
Gyroscopic motion, that's the correct name for it. Okay, so this is like a gyroscope, nuclear moment, but it's like a gyroscope, right? So spinning top is a gyroscope. So you want to know, these are all fixed in space. Okay, so there is a torque on it. So what are the usual Newton's laws? Again, what you learn in basic physics, even it's applicable even to hi-fi things.
The Latru problem.
Yes,
The Latru.
yes, that's what it is. So
In the JEE also
Rate-
it is asked. in the-
all over, but here also, JEE it is understandable. You're asking at that level. Rate of change of linear momentum is the force. Torque is the rate of change of angular momentum. You have angular momentum here, so that's the equation. I mean, you already know that. So rate of change of angular momentum, right, is the torque. So, I mean, this is well-known thing in mechanics. I don't need to sort of tell how this arises. And then you can rewrite it in different ways, right? So remember, mu is gamma j, and j is h bar I. Right? So we can rewrite this as so mu is gamma h bar I. Okay, and so we can rewrite this in terms of the gamma. So you can rewrite this as d mu dt. Right? We want to know rate of change of magnetic moment. So I can go from j to I to mu with the gamma and all that, and this will look like mu cross gamma h. Right? J is mu by gamma. So J is mu by gamma. So d mu dt is gamma mu cross h. So that's sort of the classical equation for gyroscope, or in this case, nuclear moment. Okay, in the presence of a magnetic field. Okay, so so if I have a DC field H naught in the z direction, okay, then the motion of this it's a precession motion, so it goes this way. So it's like spinning about its axis, gyroscope, and also going around the axis defined by the magnetic field. Okay, that's the motion. This is called precession, uniform precession. You can find out what the omega for uniform precession is, right? You can write the solutions for this. So it just, this omega is gamma h naught actually. So that's the classical answer, that if you have a DC field, then this nuclear moment will precess about the axis defined by the magnetic field. Next question, again basic classical mechanics. So again, those who have been doing NMR for a while, so I'm in the lab frame, applied the DC field, and I should see nuclei going this way. It's often, so RF field is not yet applied. Okay, ultimately you're going to apply an RF field, but what will the RF field do? Firstly, remember, if I apply a field, RF or whatever, in the same Z direction, it's not going to do anything. Okay, you need to get a torque. For that, you need the RF field perpendicular. Quantum mechanical equivalent is that you need transverse elements to cause transition.
So
Otherwise you don't have a plus minus, I plus I minus.
in the Z direction, it will not hinder the precision also.
So it depends on the value. Our usual RF fields are like 3 orders of magnitude smaller than this H0. So it doesn't cause much effect in a practical situation. So if you want to cause transitions, then you must have the H1 field, the RF field, in the XY plane. You can sort of understand that classically. Torque will, increase the angle, right? So if you apply an H1 field which is in some x direction, then you have to resolve the equations by writing the H as H naught along K plus now this H1 is time dependent. So I. Okay. So you need to put a sinusoidal thing, and then to describe the motion, the equation is a little complicated now. Okay. However, one can do some tricks and obtain an easier way to obtain the solution. Okay. So again, you have done classical mechanics. Those who are doing NMR know this. So what is the condition of resonance? We already learnt on that. I should have my H1 field to have a sin omega t type of term with that omega equal to this omega. Then I'm matching energy level difference by my external agency. Okay. So if I go to a frame, so I have one frame of reference which is like this. If I now go to a rotating frame, okay, which sort of rotates along with the moment, same frequency, I go to a rotating frame which is going about the, so I have my XYZ axis like this, and this is my X prime, Y prime, and also Z prime is the same. Okay, so this is going this way. Okay, then if I match the two frequencies, frequency of my RF field with the natural precession frequency, what dynamics do I see? I see this one at rest actually. You can sort of imagine that. Right? Something is going around, there's a turntable, okay, and then if something is going around at some speed of the turntable and you sit on the turntable, then of course you see that particle at rest. Okay, so this is what we are going to apply, but how do you, if you have any vector f, okay, then, right, we are interested, so in this case, the vector we are interested in is the magnetic moment vector, okay. I am interested in knowing, I am describing d mu by dt in some inertial frame, my lab frame is inertial frame. But I also want to see how to describe that in a rotating frame, right? So, how is this? So, in general, any vector, how is this connected to rate of change of a vector as viewed in a rotating frame? How is that connected to the rate of change of that vector as viewed from the inertial frame? This also, so this standard non-inertial frame, so. Not linearly accelerating but rotating, that's also non-inertial, and you have standard basic first year mechanics, what I was teaching last semester, there we did this. Anybody remember how the two are connected? Roughly?
Is it Poisson net?
Not go so far. Think.
Something like Coriolis.
I mean, if you consider another, so derivative of the velocity itself. So derivative of the position will give you a velocity. So Coriolis is when you look at the derivative of the velocity, then the pseudo forces and all that, right? So I mean, people understand what we are talking about, I hope. So one level, since we connect to usual rotating motion, so vector r, if you are looking at dr by dt in rotating frame or inertial frame, so what will be the correction factor because you will view it in a rotating frame?
Angular velocity.
So omega r will be the correction, right? Because in my lab frame, if I am seeing something static, right? If in my lab frame, I am seeing a particle at rest. So dr by dt is 0. So dr by dt inertial is 0. But if I view the same from a rotating turntable, I'll see it going the other way in a circular motion. With what velocity? R omega, where omega is my rotating frame velocity. Okay, so minus R omega. Actually, there's a cross product there. Here we have a special case where so there's actually a cross product there. And then what you're saying, the Coriolis or the centrifugal, that's when you take yet another derivative. Okay, so then you get like omega cross r, or the 2m omega v cross omega, that's the Coriolis or the centrifugal, right? So rate of change of any vector is connected. If you, as I said, if you look at dr by dt, inertial frame, then this is dr by dt in the rotating frame plus omega cross r. Okay. This you remember. So that's what gives you the v equal to r omega. Okay. And again, this is not needed right now, but what you're asking is you take now one more derivative, and then for that you will get. So what is then dv by dt? Okay, how do you connect dv by dt in inertial and rotating frames? So obviously you will get omega cross v there, and there that v again you have to combine these two, so you will get omega cross r, which is the centrifugal, and another one which is the Coriolis. So that's the basic framework. So we want to write down now for the magnetic moment vector how the rate of change is different in the two frames. Okay, so just like I wrote right now, d mu dt in the inertial frame is d mu dt in the rotating frame plus omega cross mu. But remember, this omega is the angular velocity of the frame that you chose. Okay. So now we say motion in the inertial frame is a little complicated in both this h1, h0 and h1 are present. Hopefully in rotating frame it will be easier, especially close to resonance. Okay, because it will be static sort of. So some small change, but we'll see. So we can write this as d mu dt in the rotating frame as mu cross omega cross plus. So in the inertial frame it was just mu cross gamma h. In the rotating frame you have to add on one quantity. It's understandable how you do the basic vectors. And so equation is very similar to the lab frame, except that you have added on some term, and so now instead of the applied field you have some effective field. So motion of the magnetic moment as viewed in the rotating frame will be in response to this effective field. So you can already imagine. So suppose you dealt with only h equal to, right now no RF field, just h equal to h0. Okay, then you will see if you choose the frequency correct, then this can cancel out. No? If I can choose omega is minus gamma h. Okay, I choose my rotating frame frequency as minus gamma h, then d mu dt is 0. So I see my magnetic moment just like this. Just as I said, if you have a vector which is not changing with time, then in the rotating frame it will go by, rotate by omega r. Likewise, if something is going by omega r, going with omega, so with r fixed, then if you go to a rotating frame with that omega, then you'll see it at rest. So that's what the magnetic moment vector, you'll see it at rest if you go to a rotating frame. Okay, so in other words, this is my x, y, z, and I basically will see my magnetic moment just like this forever. Okay, so we'll work with the equations, but I'll just stop in a minute. Now, if I apply an RF field along the x direction, x prime really. So in the rotating frame, my axes are denoted by x prime, y prime, z prime. So I'm viewing the problem in the rotating frame. So maybe I should just call it x prime, y prime. So if I have an AC field pointing in the x prime direction, okay, so I know the solution to this. If I have a magnetic moment and then there is a field, what is the solution? It's a precession about that field. The DC field effect has been cancelled by going to the rotating frame. I'm at resonance frequency, let's say. So, you know, this is going to be different color. So about the x prime axis, so you know, this will go like this. So I have my x prime axis this way. My y prime z prime plane is where the moment is, and it will just precess about that.
Sir, can you repeat once more how that stopped at resonance frequency?
Yeah.
From this equation.
Yeah. So if I choose omega as minus gamma h, then I get 0. So d mu dt is 0. So static vector in the rotating frame. So it's always forever, it's going to be like this.
At resonance.
At resonance. At resonance, yeah. Otherwise you will have obviously some complicated motion. So it will always be going to be like this. Now if I apply another field which in the rotating frame looks like a field which is sinusoidal along the x prime direction, okay, then this is going to precess about this x prime. So x prime is coming out of the board, it's going to precess in the plane of the board. Okay, but of course we can determine that precisely. So this is basically the classical description. If I put my RF for some time and then switch it off, then for example this can come here and then it can point along this axis, right? So often we are probing the Z component. You start with Z component to be something, and then if I keep my RF field on for some time, then it will point along the Y prime axis. If I switch it off, it will again go back to whatever equivalent, so on. So this is the classical description. It's like a gyroscope motion, and resonance corresponds to matching the RF frequency with the precession frequency, and one can describe the dynamics by going to a rotating frame and then, you know, just qualitatively even argue what happens. We'll next see the quantum mechanical equivalent. You have to write in principle Schrodinger equation. You have some time dependence of the magnetic moment operator, and then you apply RF field, how all that happens. So that will take up next time. It's about an hour or so is enough, I think, for one time. Okay. So next when we meet again, we can decide.